State machines are easily in the top 3 programming patterns of all time for me. I just love these little things. They are so useful for almost everything you can think of, from embedded systems design to video game AI, all the way to like network packet passing and things like that. They are universally applicable, but I think they get a pretty bad reputation if you've seen them in class, because they're usually introduced with a state diagram that looks a little something like this. And when I saw these for the first time, I thought, wow, how would I ever model this thing in code? It looks so complex, so abstract, but really, I'm here to tell you, state machines are dead simple, and I'm going to show you a couple of different ways that you can actually implement and model these things in real code. First, let's take a look at the program we're going to be using for the demo. This may look familiar to you if you saw my last video on object-oriented programming in C. We are simply going to extend that model into a full terminal Tamagotchi game where the character has emotions and you need to interact with it and such like this. So we're keeping track of a couple of different values down here, that being how hungry it is, its happiness, its anger, its sadness, and that's reflected in these metrics down here. These are all being tracked using state machines. And as a motivating example, I've upped the tick rate so you can see what happens when its hunger reaches 0, which you really don't want to happen, so you've got to keep feeding it, okay? There are two really important things to consider when it comes to implementing the code for state machines. The first is, what is your system actually going to do in each of these states, right? So how is state 0 going to be different to state 1? And secondly, we need to model the transition conditions. So how are we actually going to get from state 0 to state 1 in the first place? And as it turns out, people have come up with many different ways to express these in code. So keep that in mind while we look at each of these 4 different implementations. If you didn't catch my last video, this is what our Tamagotchi class looks like. And you can see here that the metrics that we were talking about before are tracked as uint8s. Now, I promised you that state machines were going to be easy, and I'm here to deliver on that promise. The way that you model a state as a concept is with an enum. So you can see here, I've just typedeffed a bunch of enums for all of the different states that our character can be in. So for example, we looked at how the character could get sad. Well, here we can see this enum, and these of course start at 0. So content, bored, lonely, miserable. And so this would be 0, 1, 2, 3. And here we see the state machine in its simplest form. It's a big old switch statement where the cases are the enums we defined earlier that represent the states of our system. So for example, here we're keeping track of this sadness state variable, and you'll notice that here our cases are content, bored, lonely, miserable. And the idea behind this is that based on what our system is currently in, we can exhibit divergent behaviors. I just want to go over these helper functions I've defined so there's no confusion about them later. sadd literally just means saturate add. So what that means is I want to add A and B together, and if there's an overflow, I just want to set them to 255, which is the max. Same thing with ssub, that's saturate sub. If they go below 0, I just want to set them to 0, right? So that means if I add 2 numbers, it's capped at 255. If I subtract 2 numbers, it's capped at 0. Now we're in a position to actually understand what this state machine is doing. So if you have a look in the content state, we are subtracting from the sadness and we are adding to the happiness, which makes sense. Now, if you come to the bored state, and in fact all of the other states for our sadness, we are adding a value to this metric of sadness and we are subtracting from the happiness, which makes sense. So the lonelier that our pet gets, the sadder it's going to become. If you look at the bored state, we are adding to the sadness at a rate of 1. If you look at the lonely state, we are adding at a rate of 4, and in miserable, well, 16. And now I have a favor to ask you. Please, please, please take what we've just done and generalize it. Do not focus on the example that I'm showing you. In any one of my videos, don't focus on the example. Please take what we learned, think about how you can apply it in other contexts, because that is the only thing that matters. What we just learned is how to model divergent behavior based on the state of our system. So please think about what else you could use a model like this for. For example, like a washing machine or a microwave. Those are 2 instances where you need to do divergent behavior and sometimes allow and disallow certain behaviors based on what the system is doing at that point in time. And state machines are incredibly powerful for modeling this kind of behavior. Have a look at this diagram here. I know, boo, we want to see code, wow, wow, wow. Just trust me, stick with this, it'll become intuitive in just a minute. So think about what we're doing here. We start off as content. Now, if there's a certain time that's elapsed, we become bored. If there's a time that elapses in the bored state, we become lonely. And if there's time that elapses in the lonely state, we become miserable. Now, if you have a look at this, any attention of any kind from any state will jump us right back to content. So that is the model that we have to implement in code for our state transitions. Now comment down to the end of our case statements and you'll see that in every state at the end, we are checking the transition conditions. And this is one of the major ways that you would see a state machine done in programming. Personally, I really like this method because it's dead simple and there's very little boilerplate. You can see exactly the information that you need all in the one case statement. There's no jumping around anywhere. So check it out, we've got this since interaction variable that we're going to add 1 to every time this state machine is called. Now this is what is going to model our transition conditions. As I showed you in the diagram, we want to model this based on a timeout. So for example, if this since interaction variable has been added to over 5 times, which means the user has gone 5 ticks before they have interacted or fed the pet, then we are going to transition to the bored state. Now down here, you'll notice we have an extra transition condition, which is to reset back to content. And you'll notice that mirrored across all of these states because like I showed you in the diagram, we always want to be able to jump back to content if the pet receives any kind of attention. So think about what that would be. Let's say we pet the pet and the since interaction reverts to 0. Now at the start of this state machine, it's going to be added to 1. So therefore our transition condition is if the time since interaction is equal to 1, we will simply jump right back to content. And you'll notice that we can also go down, so lonely ticks we go to lonely, miserable ticks we go to miserable, and then in miserable, of course, we can only go up from there. Okay, I upped the tick rate so you can see what our transitions are doing, and you'll notice that we are going fairly quickly down, 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 down. And if I do anything, so we're in miserable right now, if I do anything to the pet, so I press 4, then we're simply going to reset all the way back to content. And this is the same thing in bored, we'll go back to content, and then I'll let it go to lonely, and you'll see that we'll jump right back to content as well. So no issues there with our state transitions. In-game hunger is even more simple than the sadness one. You'll notice that we start here in satiated, and it's simply a threshold based on how hungry the character is. So if we're less than 180, we become hungry. If we're less than 100, we're starving. Similarly, we can go back up, but we can only go in one direction. Note that we can't jump from starving to satiated right away. We have to go back to hungry and then back to satiated. Now again, please, I'm begging you, generalize this. Don't hyperfixate on this being a game hunger example. Think about anything that is a threshold-based system where you could go through multiple different states. So for example, if you're monitoring temperature, then temperature drops over time. It doesn't just jump around everywhere. So you might go from extremely hot to mild to freezing, or you could even have any number of states in between. This is useful if you're monitoring the temperature of an electronic component or something like that. So please, just consider what I'm teaching you as a threshold-based state machine. We've already seen a state machine in its simplest form, which is a switch statement where you check the transition conditions at the end. But what if we have a lot of repeated conditions? In this case, doing a little bit of boilerplate might actually be better for the structure of our application. So for example, in our threshold-based state machine, where the only transition condition is a threshold high or low, we can model this in a one-dimensional transition table. A great property of enums is that they actually map perfectly to indexes that you can use for tables like this. So you'll notice here that I've defined up a little struct where we've got the floor of a state, the ceiling of a state, and the state below and the state above. So consider when our character is hungry, right? The floor is going to be the value 100. So if we drop below 100, then our next state is going to be this dot below, which is starving. Our ceiling is going to be 180. So if we rise above this, we check the dot above, which is going to be satiated. And we can model the transition here as a very, very simple ternary operator where we just grab the entry from the table and we do a couple of checks. So again, think about how we can generalize this. What we've basically done is define up a struct which holds the information about the next state and the previous state, and then we've done a little check thing down here, which really could be anything. So don't just focus on this as a threshold thing. You could define anything in this struct, and as long as your next transition function returns the next one according to your rules, you can really model this in any kind of way for any kind of state. This is the benefit of all of that boilerplate. You remember how long this sadness one was, right? Like it's pretty long and you have to go and check the conditions right in here at the end of every case. Well, this one is very, very simple and very, very lean, and there's only one place where the next state is calculated. So you don't have to go and see what state you're in and then look at the logic and then pass the logic. There's one place where you do this, and the function is very, very lean. And the business logic of the hunger is all about the anger value. So you can see if we're satiated, we'll add to the happiness, subtract from the anger. If we're hungry, we'll subtract from the happiness and add to the anger. And it's just going to get worse if we're starving. Now, I'm going to get some actually's in the comments who are going to point out that you can probably collapse a bunch of these states and just do some kind of lookup table to get these add and subtract values. There's a similar argument you could make for this one as well. And the answer is yes, actually you can do that, but this is for illustrative purposes, okay? I want to spell out all of the states in all of their verbosity so that people can get an idea of the structure of these kinds of things. So that is the reason why I have not collapsed this into a lookup table. At this point, I want to take a step back and look at how the demo is actually working as a whole. So we've covered two of these state machines. We covered the hunger and the sadness. But how are these actually getting executed? Well, as it turns out, what we have is a high-level game state machine, and we'll get to that in just a minute, which gets executed on every game tick. You've heard me reference game tick before. Literally what that just means is how many times per second are we going to compute these state machines. So for example, if we have a tick rate of 1 hertz, that means that these state machines are getting run once per second. And you'll typically see these state machine functions being run either through a loop or based on an event. So consider in an embedded system, we have the while1 loop, and you might have a couple of different state machines that are being triggered by that while1 loop constantly. So the state machines are constantly going through, checking their transition conditions, and then going off and doing their own thing. Now you could also have event-triggered state machine runs, for example, based on an interrupt. So you get an interrupt in, like let's say you receive some data over the wire, and you have a state machine that you're using to pass the data. So in that case, it doesn't make any sense for you to trigger that on a while1 loop if your data comes in an interrupt. A perfect example of the event-based state machine trigger that I was talking about just before is T-Game Peer. I don't think I mentioned this yet, but the game is actually multiplayer, and I'm using a state machine to keep track of what the peer is doing. So if you have another Tamagotchi that wants to connect to your world, then we have to keep track of what that peer is actually up to in its own world, because it's got its own user, it's got its own emotions, it's got its own interactions. So the network kind of has to decide what's going on there. And so what happens to trigger this state machine is a network receive event. So if we receive from the network, that is the only time this state machine runs. It doesn't run any other time. And you can see that it does some packet passing, and based on the packet that it receives, it's going to set the peer state. So for example, the peer says hello, we go to idle. The peer sends a chat message, we go to talking. The peer says that it's feeding, then we go to the peer is eating. And consequently, the peer actually feeds us as well. So we both go into the eating state. If the peer is playing, that's a solo activity, so we don't partake in that. We just track that that's what the peer is doing. And so you can kind of see we can track events based on this event-triggered state machine run. This is only being run when we receive from the network. It's not continuously being calculated once per game tick like the other state machines in our system. Worth noting. But in our demo today, we are going over the loop triggered option, where these state machines are being called approximately once per second right now. Now, I mentioned previously that we have a game state machine, and this is where things for our demo get really interesting. The game state machine focuses on what action the character is currently performing, and based on this, it may be appropriate for us to compute hunger, sadness, or neither. So for example, if it is eating, there is no point in computing the hunger. So if the character is eating, then we're not going to compute the hunger. Similarly, if the character is playing, so you pet it and it starts playing for a little bit, then there's no point in computing the sadness because we assume that it's just going to be happy for a little bit. And you can see this game action state machine based on input from the player. So we default to none, and in none, we are actually computing both the hunger and the sadness. Then if we feed it, it starts eating, then it can time out back to none. If we pat it, it starts playing and it can time out back to none. Now, of course, if we feed it while it's playing, it'll go eating. If we pat it while it's eating, it'll go playing. And so here for our demo, we form the idea of a child and parent FSM. So game is the parent FSM, and it determines the conditions under which its child FSMs can run. This is part of a broader concept called interacting FSMs, but I'm not going to get into that too deeply in this video here. Just keep in mind this parent-child relationship for our specific demo. Let's see that in action. So right here we've got our character. If I feed it pizza, for example, you can see here it starts eating for a little bit, it should be about 5 seconds, and then this will go ahead and disappear. When it disappears, it means our action is back to none. And another interesting thing you can see is that you can see our stomach decreasing by 1 each tick. Well, if I start feeding it, then that stops decreasing while we are eating. And you may imagine that's hard to model, but really it's not. What we're going to do is extend our one-dimensional table from before to instead be a two-dimensional table. And what we've got here is basically transitions based on external events. This is a very common way to model things in embedded systems, for example. So what we have is you define the action, which is our action state, basically. So what we talked about before, we've got none, we've got eating, we've got playing, and then based on an external event that comes in, we can select a new state. So these are all identical at the moment. I've just done them all out verbosely for demonstration purposes, but you can see here, if we are in the none state, we get a feed event, we jump straight to eating. We get a pat state, we jump straight to playing, and then we get a timeout, we jump back to none. And you can see this is the same thing for all of these because, of course, that is how all of them work. If you think about this more generally, where you basically just have state transitions based on external events, you can model almost anything this way, and that's why it's very commonly used. So please, when you're looking at these examples I'm giving you, take a step back, detach them from the specific example, and think about how the concept could be used more generally. Now have a look at the switch statement for this example. The whole idea behind this is that we don't actually want to consider calculating some of the emotion values based on what it's doing. So for example, we have this run hunger state machine that we looked at before, right? If it's currently eating, it makes no sense to run the hunger state machine because the hunger state machine, as we saw before, decrements the hunger and then does happiness calculations. It just does not make any sense to even begin to calculate those values if the thing is currently eating. So we simply omit it from the logic that happens in this state. Similarly, if we're playing, we have this sadness state machine here. It doesn't make sense for it to run sadness while it's playing because we just assume that it's always happy while it's playing, but we do care about the hunger in this instance. Then of course, if it's not doing anything, then we're going to run both hunger and sadness. Now the question I know you're asking is, okay, this is cool. We've got a little table where we can map events to the states, but how do we actually tell the system that an event has occurred? Well, that happens with this T-game action right here. So in our Tamagotchi struct, we basically just keep track of what action is currently being performed. That's where the actual game action is stored. Now, literally all we do here is we grab the action table, we take the current action, and we pass in this action event with an E. So to show you what that looks like, let's say we get a timeout, right? So we're playing the game, you can see we've got the action ticks increasing by 1, and let's say this gets to be more than whatever tick rate that we've specified for how long it should be playing. Then all we have to do is call tgame action timeout, right? And so we pass in the Tamagotchi object, which holds the action, because if we go back up to this, you can see here, it's going to recalculate the action based on the action table, the current action, and then this event that we pass in, which you saw just before was the timeout. Another very important thing that this game state machine does right at the end is it calculates the overall emotion that the character is experiencing, and that is what's displayed on screen, whether it's happy, sad, angry, or if it has met an untimely end. Now, looking at the emotion calculation function, you may think this is a state machine, but trust me, it's not. It's just trying to fool you. I get that it kind of looks like a state machine. We have some conditions, and then we have this state of the emotion that we transition to, but really this is not a state machine because the previous value does not determine the next value. It is simply a maximum threshold calculator. So what we're trying to figure out is which of these three emotions is currently winning, and then we just jump straight there. So it's not really a state machine because the previous state does not determine anything about the next state. It's just a calculation that's run every tick. Now, I promised you 4 different implementations of state machines, and while we have covered 4 state machines in total, those of you who have been paying attention will note that we've only covered 3 types so far. That being the simple case statement, and then you have the transition logic at the end of the case statement. There's the one-dimensional table, which was the second one we covered, then the two-dimensional table. And I have saved the worst for last. What I mean by that is because I know how the viewer retention goes on YouTube, I've saved the state machine implementation that I hate the most for last because I want people to use it the least. But if you're seriously wanting to learn about state machines, it's a good one to know, so I'll let you in on it anyway. Because our characters are a little bit weird, if they are eating a hamburger, then they like to eat it one layer at a time. So first it's wrapped, you gotta unwrap it, then they eat the pickles, then they eat the tomato, then they eat the lettuce, the patty, and then the burger is gone and it can't be consumed anymore. So let's look at the implementation of this and what I hate about it so much. But we use those enums for something absolutely horrific, which is a lookup table of function pointers. Now look, okay, there are good reasons to do this method, which is why I'm teaching it to you. But in general, I really dislike this because in a lot of cases, it just adds unnecessary indirection. If I want to see what these all do, I have to jump all over the place to different functions. It's just not very easy to follow, and it's hard for the linker to optimize. So oftentimes this is going to be slower than the other implementations we've covered, especially the direct switch case statement where the transition logic is at the end. That's very, very easy to execute. Although one good thing you can say about this is that the state machine function that actually runs the states gets very, very simple because all it has to do is just go ahead and call this function, and this function is going to return the next state after it's done. So each of these function pointers is going to execute its behavior, and then based on the conditions that it evaluates inside the function, it will return the next state for the machine. Now in our case, these are all very simple, right? So the wrapped is just going to return the next state, and notice that it doesn't have a feed call because of course there's nothing for it to feed. We're just unwrapping the burger. So here you can see we are feeding, and we're just going through the next one. Now, when we get to the patty, the divergent behavior we're going to do is let the user chew it multiple times. So that's how you can model the divergent behavior with the function point method. All of this custom logic goes inside the custom function, and then you can evaluate some condition to return the next state. In our case though, this is a very simple state machine of just go, 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 go. The only kind of complicated part is this choose because of course we are chewing until it's all gone. Now I said there are some valid reasons to use this method, and of course the first one that comes to mind is if each of these individual states is absurdly complicated. So think about a video game enemy AI. Inside the video game enemy AI, depending on what it's doing, it could even have multiple child state machines that are running for, like if it's alert, searching for an enemy, if it's idle, waiting for something to pop up. Each of these states might be a couple hundred lines long or something like that. And so if you try and model it in one of these more traditional state machines, it's going to get to be a very, very long function. And so it might be worth hiding it inside a layer of indirection like this. So it is a legitimate technique, and maybe I was being a little bit harsh, but what I want to stress is please, when you want to add extra indirection, use it with discretion, use it wisely. That's going to wrap up our video, guys. I hope you enjoyed, I hope you learned something about state machines, or maybe seen a state machine implementation that you haven't come across before. Let me know how long you can keep your Tamagotchi happy in the comments below. Thanks.